Okay, so we are going to study what happens when electromagnetic wave cross boundary, so from one medium to another medium. So this session is about reflection and transmission at a normal incidence. So I'm going to have a summary of wave equations, and I'll also summarize some key electromagnetism theories that lead to boundary conditions. So we are going to use them fairly differently compared to how we use magnetism theories before. So I hope this summary would be helpful, and then also at the same time you learn something new. Okay, so summary of wave equations. First of all, we have electric field and magnetic field. So the complex valued electric field, this equals to polarization and then propagation function I kappa z minus omega t. So I must emphasize again here that the polarization is complex valued vector, so it has x component, y component, but it as a whole, the polarization is a constant because we modulate our message onto polarization. It shouldn't change over propagation of distance and time. So this is a vector, complex valued vector, but as a whole is a constant. And then the second part, the propagation function, is a scalar function, but it varies with distance and the time. So z and t are variables, and this second part is scalar, but it's a function. And then for magnetic field, we know that in order to satisfy Maxwell's equations, we must have magnetic field, electric field, and direction of propagation perpendicular to each other. Also, the magnitude of the electric field divided by speed of light equal to the magnitude of magnetic field. So magnetic field really is quite weak. So we have magnetic field equals 1 divided by c, propagation direction cross the E field. So here in free space, we have c equals 1 divided by mu 0 epsilon 0 square root. So now what happens when we have linear medium? So the EM wave travels at a slower speed in linear medium. So we need to change, we need to modify the magnetic field. Here we have magnetic field equal to 1 over the speed of the wave in that linear medium. And then still the propagation direction cross the E field. So the speed here equals to 1 divided by mu and epsilon. So permittivity and permeability of different materials, they are going to be different. So normally the speed is slower than speed of light in linear medium. And then we have some basic relationships between parameters that we're going to use quite a lot in this session. So I have parameters. So first of all, here we have omega, which is angular frequency. This equals to kappa v. And then we have, so how much slower of this speed compared to speed of light in vacuum, in free space? We have this index of refraction equals to c divided by v. So now we are going to study, reflection and transmission at a normal incidence. So suppose we have linear medium 1 on one side, and we have linear medium 2 on the other side. So I have the boundary here. And now we know the direction of wave propagation is that direction. So it's, it's at a normal incidence. So we have incident wave. And then we have transmission. We also have reflection. So reflection actually happens at this point and then towards the opposite direction to the incident wave. But in order to present it more clearly, I draw it from here, coming back, we have reflection. So for the two media, basically they have different permittivity, permeability, wave number, and index of refraction. So basically you have different epsilon 1, mu1, kappa 1, and then n1 on one side. And then we have mu2, epsilon 2, mu2, kappa 2, n2 on the other side. But the same thing should be omega. So they have the same oscillation. The oscillation doesn't change across boundary. So angular frequency doesn't change across boundary. So that would give us some useful relationship. Another thing is, so the incident wave is what we generated. We put it there. So we should know its magnitude. Our task is to find out how much wave is transmitted and how much wave is reflected. So we'll assign a ratio. So some ratio R of E0 is reflected. And then some ratio T of E0 is transmitted. So our objective is to express R and T by these medium parameters. So as long as we know what medium it is, we should know how much wave should be reflected, how much wave would be transmitted. And also we need to prove, conservation of energy, because power doesn't just go away randomly or just increase from nowhere. So some energy, some intensity will go to transmission and some intensity will go to reflection. So let's plot a 3D diagram. So I have the surface like this. And suppose the wave should propagate down that direction. And then we have electrical field that's going to be polarized in the x direction. And then based on right-hand rule, the magnetic field will be, the direction of magnetic field will be in the y direction. Okay, so now we have incident wave coming down in the direction z at a velocity v1. So we assume the electrical field, the polarization is in the x direction. So we have EI like this. So based on right-hand rule, from the propagation direction across electric field, the magnetic field is pointing towards y direction. So we have magnetic field BI. Okay, and then we have transmission. On the other side of media, the speed would become V2. And then the electrical field would change as well. We have E T. And then we have the magnetic field, which is BT. Reflection. For the reflection, the wave would go back. So the velocity in the media on the left-hand side is still V1. So we have V1. And then the electric field direction shouldn't change because we modulate our message onto the electric field. The message shouldn't change after reflection. So ER. So for example, when you look at the mirror, the light reflects back to your eyes, and then you get the information about your image. That message shouldn't change after reflection. So now based on right-hand rule, propagation direction across electrical field, we have the magnetic field direction is opposite to this, which is minus y direction. This is a geometric necessity. Here there is no change of direction, but here reflection we have change of direction for propagation, but message doesn't change, so something have to change. That would be the magnetic field. That's just what happens. So BR. So now we are ready to write the wave functions for all the three waves. So first of all, we have the incidence. So I have EI equals to some magnitude E0. We generated the light and put it there. So this is what we know. And I propagate down Z direction. So I have I kappa 1 Z. So on left hand side we have kappa 1 minus omega T. And then the polarization is in the X direction. We have like this. And then the magnetic field, we have 1 divided by V1, and then propagation direction cross electric field. So we have 1 divided by V1, and then E0, and then EI kappa 1 Z minus omega T. The propagation function is the same, but the direction of magnetic field is y direction. Okay, then next we have reflection. So we have ER. So the magnitude is R E0. So I have R E0. And then we have a propagation function. So the propagation direction is opposite to the incident wave. So I have I, and then minus kappa 1 Z, and then minus omega T. Polarization is still X direction. Devil is in the detail. So yeah, so check with the figure. So it's impossible to, without looking at the figure and then you write everything. Okay, so BR would be equal to 1 divided by V1. And now the propagation direction is minus Z. So I have minus Z direction cross ER. So this equals to R divided by V1. And then the propagation function, E0, the magnitude, and then propagation function I minus kappa 1 Z minus omega t. And then direction is the negative y direction, so I have y, and then here I have negative. Okay, and then the third one is transmission. So I have ET. The magnitude is some T E0. And then we have EI. The direction is K. Direction is Z. But the wave number here is kappa 2. So I have kappa 2 Z minus omega t. And then polarization is still X direction. And then we have the magnetic field, which equal to 1 divided by V2. This is linear medium 2. And then propagation direction is Z. So Z cross ET. So this equals to T divided by V2. And then E0, and then EI kappa 2 Z minus omega t, and then Y. It seems things getting a little bit complicated, a little bit messy, but actually your equations are very easy to check, because so first of all, you need to get all the electrical field correct, all the wave functions for electrical field correct. So this is the most important starting point. And then from here to reflection, the direction is the same. The propagation direction is different, so you need to replace Z. So you need to replace Z by minus Z for propagation function. And also the amplitude, you should replace E0 by R E0. So here you have R E0. And then the rest should be the same between these two E fields. So that's quite easy to check. And then between the incident wave and the transmission wave, so here you have a magnitude E0. Now you should have T E0, because only some ratio T of the magnitude is transmitted. And then kappa 1 should be replaced by kappa 2. And then the rest is the same. And then based on electrical field, you calculate the magnetic field. That would be more straightforward. So for magnetic field, the magnitude is very easy to calculate, which is electrical field divided by the speed in that medium. And then the direction is always helpful to check with your right-hand rule. So you separate, direction and magnitude. So the key point is getting this right, and then you replace things based on this figure, and then you can check your equation. So our goal is to express express R and T as function of medium parameters. So we need to establish relationship between all these three waves. That's why we need to look at boundary conditions, because this boundary is where the three waves they meet. So normally for boundary condition, we have this surface of boundary, and we observe a pillbox. So the pillbox would have area above and area below, and the thickness is infinitesimally small. So when we observe the area above and also the area below, rule of thumb is that when we observe the area, when we do area integral, we are observing how the normal component of the field changes when it crosses the boundary. So we are investigating the normal component of the field. Let's look at electric field first. So we have the E field. And the most important law here is for the surface integral, we have Gauss law. It is generalized in linear media as the closed surface integral of the E field equal to total free charge enclosed divided by epsilon. So on both sides, they don't have the same epsilon anymore. We have epsilon 1 and epsilon 2. But the electric field on both sides, they share something. For the area enclosed, we share the total free charge enclosed. So if we move epsilon to this side, we'll get the first boundary condition, which is epsilon 1 E1 normal component equal to epsilon 2 E2 normal component. So it is a normal component because when we observe the area, so here the dot product between the field and the area vector, the direction is perpendicular to the surface. So when we do the area integral, we are investigating the normal component of the field. So what happens when we observe the parallel component of the E field? We have this surface for boundary, and then we observe pillbox. So, rule of thumb, when we do, this is the same pillbox. So thickness is infinitesimally small, but we have area above, area below. So when we observe this closed path, so when we do line integral, we are observing the parallel component of the field. So the width here has physical meaning. There is a width, but the thickness here is infinitesimally small. So when we do the line integral, we are observing the parallel component of the field. So for the line integral, we have Faraday's law for the E field, where we have the closed line integral dl. We call fundamental theorem for curl. So we have the surface integral curl of E dA. And then Faraday's law tells us that curl of E equal to minus dB dt. So the varying magnetic field generates electric field. So we have minus d dt, and we still have the surface integral from here, and then we have the magnetic field dA. So here we can see that originally we want to observe this closed path, but the fundamental theorem and Faraday's law transform this into a surface integral into the flux of B field. So what is the flux of this area enclosed by this closed path? That area is infinitesimally small because the thickness is infinitesimally small. So the flux of that area should equal to 0. So the area doesn't have any physical meaning. It's not meaningful at all. But only the width is meaningful because the thickness is infinitesimally small. So here we have the parallel component E1 equals E2. So when we do the path integral, we are observing the parallel component of the field. So next we have B field. So when we consider the normal component, we do the surface integral again. So what is the value for this? So first we call the fundamental theorem for divergence. We have the volume integral divergence of B, and then d tau. So this would be 0. Divergence of B field is always 0. So here the flux of E field is determined by the total charge enclosed, but there is no magnetic charge wherever it is. Wherever there's no magnetic charge. So divergence of B always equal to 0. So this gives us the normal component of the B field on both sides. They equal to each other. So we have the normal component of B field investigated by surface integral as well. And now, what about line integral? So we have Ampere's law, and we have Maxwell's modification. So basically what we have is for line integral, closed path integral, we have mu and then total free current enclosed plus Maxwell's modification, where the B field is generated by the change in magnetic field. So we have mu epsilon and then surface integral so mu epsilon d dt and then surface integral E and dA. Yes. So let me erase this to avoid confusion. Okay, so we are investigating the path integral, but now here, because of Maxwell's fixed, the second term is flux, and flux through this area enclosed by the closed path is 0 because the thickness is 0, area is infinitesimally small as well. So this term equal to 0, but this term has value. So now mu1 and mu2 on both sides, they are different to each other. So we should move mu to this side, and B1, B2 they are different. But they share something common, which is the free current enclosed. So here we have 1 divided by mu1 B1 parallel component equal to 1 divided by mu2 B2 parallel component. So by investigating this closed path integral, we studied what happens to the parallel component of B field. So I hope this summary from the electromagnetism series to boundary condition is clearer this way. Let's summarize all the boundary condition here. So, in summary, so the first boundary condition we have epsilon1 E1 normal component equal to epsilon2 E2 normal component. Then let's write normal components together first. We have B1 normal component equal to B2 normal component. And the third boundary condition, we have E1 parallel component equal to E2 parallel component. And then the last one, we have 1 divided by mu1 B1 parallel component equal to 1 divided by mu2 B2 parallel component. So these two are about normal component, which is also called perpendicular component. Perpendicular components. And these two, they are parallel components, which is also called tangential components. Okay, so now we have all the boundary conditions. We need to put the fields on both sides to these boundary condition equations. Okay, now we are ready to calculate R and T. So what we need to do is we need to put these wave functions into boundary conditions. So let's look at the first boundary condition, which is a normal component of E equal to each other, and second is normal component of B equal to each other. So what we have here is the E field and B field on both sides. They only have parallel component. There is no normal component. So this is the plane, and E field is polarized in the x direction. They are all parallel to the boundary. And the magnetic field is either towards in the y direction or minus y direction, that also parallel to the boundary. So the first two boundary conditions just naturally trivial. So we only have 0 equal to 0, 0 equal to 0, because B field and E field for our normal incidence case, there is no normal components there. This one though, we have parallel components. So parallel components of the E field is just an E field because x direction. And they equal to each other as a boundary. What is a boundary? Boundary is where z equal to 0. So they should equal to each other at z equal to 0. So let's write this down. So the third boundary condition was yes. So we have E on the left parallel component equal to E on the right parallel component. So first step, what does this mean? This means on the left hand side, we have incident electric field, and we have reflected electric field. As a boundary, we have z equal to 0. So this should equal to, on the right hand side, we have the transmitted electric field. As boundary, we have z equal to 0. So if we put all of these equations together, so we have EI plus ER equals ET, but we need z equal to 0. Then we would have some relationship between R and T. So let's put them together. So the second step, so we have EI, which is E 0, and then propagation function z equal to 0, so we only have minus omega t. So this is an incident electric field at z equal to 0, and this plus r e 0 e minus I omega t. So this is a reflected electric field. And then we have this should equal to Et, so T E 0 E minus I omega t. So it turns out that this whole thing, and this whole thing will be cancelled. What we are left with is a very neat version of the relationship between r and t, which is just 1 plus r equals t. So this is very promising because if you have another boundary condition, if we apply another boundary condition, we have another relationship between r and t, and hopefully we can solve r and t. So the fourth boundary condition, we have 1 divided by mu1 b1 parallel component equal to 1 divided by mu2 b2 parallel component. First step is usually universally true that almost all linear materials have mu1 approximately equal to mu2. So this is actually simplified or boundary condition, which becomes B1 parallel component equals B2 parallel component. So what does this mean? The second step, so similar to this, but we have B. So we have the incident magnetic field, and then we have the reflected magnetic field on the left-hand side. At the boundary, we have z equal to 0. So this should be equal to Bt. So the transmitted magnetic field at z equal to 0. So we have all the wave equations here. We only need to set z equal to 0. And then on the left-hand side, we add Bi and Br together. This should equal to Bt. So let's extend this. So the third step, we have 1 divided by V1, and then E0, and then E minus I omega t. So that is the incident magnetic field. And then minus R divided by V1, E0, and then E minus I omega t. So that's a reflected magnetic field. And this equals to T divided by V2, and then E0, and then E minus I omega t. So now all of this will be cancelled. So I have another relationship between R and T. It's given by 1 minus R divided by V1 equals to T divided by V2. So now we have two equations to solve two variables. V1, V2, they are parameters of the medium. So based on this, we have V2 multiply 1 minus R. V2 multiply 1 minus R will equal to V1T. What is T? T is 1 plus R. So T T V1 and equals to V1 1 plus R. So it's very easy to solve now that R equals to from here and here we have yes, so we have v2 minus v1 divided by v2 plus v1. So we move v2r to right hand side and v2 minus v1, yes. And oh, by the way, so we have the definition of index of refraction equals to C divided by V. So N is inversely proportional to V. So naturally, this one can be written by N1 minus N2 divided by N1 plus N2. So that's R. And T equals 1 plus R. So we have T equals to 2v2 divided by v2 plus v1. So 1 plus is yes. And then we have this equals to 2n1 divided by n1 plus n2. So this is a very important conclusion, because now if we go back to the wave equation, if we know the incident wave, that's what we generated, we put the wave there. And then the reflected wave and the transmitted wave, they can be expressed in this way, where R and T can be expressed as a function of, the medium parameters. So as long as we know what the mediums are, what the media are, we can always express, the wave function for reflection and wave function for transmission. We know how much wave is propagated as reflected wave and as transmitted wave. So some properties that we can observe from here. So basically, R tells us that ER, so the reflected electrical field, equal to R EI. So if I have N1 bigger than N2, these two will be in phase. Otherwise, there will be pi out of phase. That's some interesting observation. And now finally, we need to prove, in order to prove that these expressions, they are correct, we need to prove, there's conservation of energy. So there's no power just randomly lost, and there is no power just randomly, added to these three waves. So we need to calculate intensity. So for the incident wave, I, so intensity of incident wave should equal to 1 divided by 2, and then epsilon 1 V1, and then E0 squared. That's the amplitude and permittivity and velocity. And then intensity of the reflected wave, we have 1 divided by 2 again, and epsilon 1 V1, and then R squared E0 squared, right? So we have R EI. So the transmitted wave, we have IT equals 1 by 2, and then epsilon 2 V2, and then T squared E0 squared. Right, so now we have the definition of reflection coefficient, which is given by R equals IR divided by IT. So IR divided by IT is just R squared. So I have N1 minus N2 divided by N1 plus N2 squared. And now the transmission coefficient, we have T equals I T divided by I. So this equals to, from here to here, we have epsilon 2 V2 T squared divided by epsilon 1 V1. And now, so this is kind of a parameter relationship. Let's do another one. So we have V, we have V equals to 1 divided by square root of epsilon mu, right? So from here we have V square equals to 1 divided by epsilon mu. And then we have epsilon V equals to 1 divided by mu V. So here we have epsilon V. We want to transform that to mu V because we know here, where was it? Oh, here. The material would have roughly the same permeability. So this would equal to mu 1 V1 T squared divided by mu 2 V2. And now the two materials that have roughly the same permeability, so V1, V2, and the V is inversely proportional to N, so here we can have N2 divided by N1 and then multiply T squared. So eventually T equals to 4 N1 N2 divided by N1 plus N2 squared. So if you add these two together, it's very obvious that you have R plus T equals 1. Conservation of energy. So this also confirm that all R and T here they are correct. Otherwise, we wouldn't have conservation of energy. This is quite a journey. It's quite a journey. But if you think about this, the whole process has 3 major steps. The first step is to express the wave functions. So you only start with the incident wave function, and then you have a lot of methods to check that you get it right. You need to read from the figure instead of just working on the equations blindly. And then you need to list all the boundary conditions. So all the boundary conditions, they are very classic. They are from electromagnetism theories. And finally, you put all the wave functions into boundary conditions, and then you solve R and T. You can only confirm if they are correct or not by confirming there's conservation of energy. So yeah, it's quite a journey, but I hope it's you'll get time to derive all of them by yourself, and that would be really good. Okay, thank you.